All right. Hello, everyone. Thank you for your attendance. Today we have Dr. Cin-Ty Lee. Cin-Ty is a professor of geology at Rice University. He received his PhD from Harvard and bachelor's from UC Berkeley. His research primarily focuses on the origin of continents, volcanism, and ore deposits, and birds, but that's not in his bio. That's just my knowledge about him. Today he'll be talking to us about ore deposits. So whenever you're ready, Cin-Ty, please begin.
Yeah, okay. So thank you. Let's see here. Thank you, Nur, for inviting me. And too bad I can't be there. But anyway, so I'm going to talk about copper porphyry deposits. And this, of course, is a really deep subject with so many people over the years working on it from different angles. And I've come at it fairly recently, at least within the last 10 years. And my views may not fit exactly some of the traditional views. So that's hence the title here is a perspective or my perspective. And I'm not going to really answer everything, just kind of talking about how one might want to look at certain types of ore deposits. Now, I'm going to show these two figures here, which at first like don't seem to be related to the talk or even to each other. And the main thing I want to show you here is this on the right, these big, beautiful pegmatite crystals of tourmalines and feldspars and quartz from the Pala District in Southern California. And then on the right, this is a hypabyssal magmatic rock, an intrusion, but it has this texture that we call porphyry, where you get large feldspar crystals set within a relatively finer grained ground mass. But what they have in common is that they both have these large crystals, and we have recently been very interested in crystal growth rates, and that in the end, I'll show you how that may be relevant to uh, at least part of the story of the copper porphyries. And so, if you go into Wikipedia and you look at how do big crystals grow, or they'll tell you that they sit quiescently in an environment for a very long time, so that allows them to grow larger and larger. But what I'll tell you is near the end that probably is not correct, that the bigger you are, the faster you actually grew. And that becomes potentially relevant for ore deposit formation. But let me come back to copper, and I'll tell you what copper porphyries are. These are some old slides. I kind of got interested in the economic geology a long time ago. But this is just showing you our projected consumption of copper. Of course, there's a while, so it's in 2018 what they thought in terms of copper that we were going. We weren't even in the energy transition at that time. And then on the right here is showing you, the projected demand, but also the projected supply of copper from the reserves that we had at the time. And it was thought that you had a big gap here, and you had to make up for that through new exploration or conversion of resources to reserves, of course, at an increasing cost. And so as we move into the energy transition, of course, it's not just lithium and cobalt that we need for batteries. We need to revamp our electrical grid system, and that means copper everywhere, including the United States. So my interest is in more of the academic pursuit of how do ore deposits form. And so basically, if you're looking at copper, the average concentration of copper in the background rocks, granodiorites, granodioritic crust is about 30 parts per million, but what you want to get is a refined product that is 100 weight%. And so it takes an immense amount of energy to just go and process the earth to get you that. So what we hope for is that geological processes, nature, will will align, the stars will align in such a way that pre-concentrates and scavenges this really dilute copper and then pre-concentrates it into and immobilize it into some reservoir, much like we think about oil, right? There's a source rock, dilute source rock, and then it comes into concentrate into a reservoir. Well, we want the same thing in the case of various metals. And so if we can even concentrate up to like a tenth of a percent, we're happy. That's like a 10,000 fold enrichment here and really saves us a lot of energy. And at that point, we call it an economically viable ore deposit. And so this talk will focus on the process of mobilizing dilute copper and transporting it and then finding a way to immobilize it so that we can mine it. And so this is some artwork from Dylan Marsh, and he's showing you here a copper egg sculpture set within a big giant mine here. And the idea is to show you that even in an ore deposit, this is how much you have to excavate to get this amount of copper. So we really rely on nature to help us out to get these enrichments. So copper ore deposits, there are a number of different copper ore deposits, but one of the very important ones are porphyry copper deposits. And certainly in the US, in the Americas, South America, the majority of the copper deposits that are mined are of this type. The ones in Africa are not porphyries, they're something else. And I won't talk about those, but these are associated with volcanic systems. And they're almost always associated with magmas or host rocks that look like this, these porphyries with this particular texture. Now, not all porphyries have copper deposits, but almost all of the magmatic copper deposits of these types are associated with porphyries. That's why we call them porphyry copper deposits. And these intrusions typically are shallow. They're in arcs, volcanic arcs. They're a few kilometers below the surface. And the mineralization actually happens at the top of these intrusives, these stalks, these shallow level intrusives. So they come up, fracture the country rock. The country rock may be igneous rocks, maybe metamorphic rocks, but and fluids are released from the top of the stalk and they migrate into the country rock and they precipitate the copper. They scavenge the copper and they precipitate in here. And there are a lot of things going on here. There's a lot of source of water. Groundwater can be pulled in through hydrothermal circulation, meteoric waters, I mean. And then there are magmatic waters that directly from the magma itself that exsolve, and they're the ones that carry, presumably, the copper. And that interaction can lead to very complex behavior in this regime where things are deposited. But these are essentially the roots of volcanoes. If these go up to erupt, you lose it all. If they're too deep, you don't get the mineralization or the degassing. So there's a sweet spot of a few kilometers below the ground. And that's where the copper eventually becomes in this cupola. And for you to mine it, you have to have the right conditions too of erosion, where the weathering regime has exposed this to the surface, but not so much that it completely erodes it away, that it's completely gone. So that's sort of at the surface, kind of at the exit of these, where the magmas are transporting themselves across the crust. But there's also another part of the story for copper is, why do you get this enrichment in copper up there? And it comes down to within the community, the issue of source versus process. And so if you zoom out, look at the whole big picture here, there are some folks that believe that the oceanic crust becomes altered and may even be enriched in copper a little bit through the alteration. And as it subducts, here's a zoomed out version, it melts or it undergoes metamorphic reactions and releases this copper, which enriches the mantle wedge. And then that goes on to bring copper-rich arc magmas to the surface. There's another extreme, whereas this doesn't matter so much in terms of where the copper is from. There's nothing unusual about copper concentrations, but that somewhere along this process, the conditions are such that this copper becomes more easily scavenged, removed, and transported to the surface. So source versus process. And for those of us interested in any types of ore deposits, particularly these magmatic ones, it's a tough problem because we have to look at from the big picture, the whole cycle, um, all the way down deep, and then all the way down up to the shallowest levels where the final reservoir might be. So we're talking going from length scales of hundreds of kilometers down to length scales, of course, at the meter scale. So this is a cartoon kind of which we'll end with, but I'll show it here so you see it now. And we're going to talk about different scenarios, source versus process, where the source, the parental magma, is already enriched in copper, or the process scenario where there's nothing unusual about the magmas in terms of copper, but they have unusual properties, the magma, that allow otherwise normal copper to be scavenged, moved, and then concentrated. And so let's look at the distribution of copper deposits around the world. And you can see here, this makes no distinction on the geologic type of copper. It's just all copper deposits. So you have some in Africa, but they're not many, and they're associated with these sedimentary hydrothermal deposits. But if you look around the world, most of the copper deposits are here on active margins. This is the Mesozoic active margin, the Cordillera, North American Cordillera, and then the present active Cordillera in South America. So these are continental arcs. And then if you go to Eurasia, you find them in the Paleozoic arcs right here, up in the in this region over there. You find them in the Philippines, but you don't find them in Japan. You don't find them in the Marianas. So they associate with subduction zones, but it appears to be not all subduction zones. Continental arcs, or where the upper plate is very thick, like in the Philippines, but not in island arcs. And this one is just showing you copper deposits as a function of time. And part of this is really related to preservation. These old ones get eroded away and you don't see them. But you can see that there's a peak here in the Jurassic and Cretaceous, and that's basically all of this stuff over here when the North American Cordillera flared up in arc magmatism, continental arc magmatism. Now, the other interesting thing, and this is from Lukes et al., is that economic geologists will often use indicators. We often don't know why, and sometimes it doesn't matter why. It's just there's a pattern. And so if you look at strontium-yttrium ratio, it's not important what those elements really are for now. And this is silica, so you have rhyolitic guys and basaltic guys here. But you'll find that these are for magmas. The magmas that host copper porphyries almost always have high strontium-yttrium ratios, and the magmas that don't host copper porphyries don't have high strontium-yttrium ratios. So it turns out this ratio, as I'll show you later, is sensitive to the presence of garnet somewhere in the petrogenetic history of the magma. And garnet is something that's stable mainly at high pressure. And so this is a signal that maybe there's a connection between the thickness of the crust where magmas pass through and differentiate and crystallize and the origin of copper porphyry. So crustal thickness. So all of a sudden we're beginning to think about a structural control, not just petrogenetic, on origin of copper porphyries. So I'm going to go back in time when we first started this, and we're still working on it because there's so much interesting things to do. But in 2012, we saw this, what we thought was kind of a paradox. It was a very obvious, in-your-face paradox, but I don't think anyone had really decided to just say it out loud that we got a problem. And the problem is this, that as I showed you before, copper porphyries are associated with continental arcs, where the upper plate is a continental plate or a thick arc. So this would be like the Andes, the Western North American Cordillera. But if you look at the magmas, the host magmas in terms of copper, and you want to look at this magnesium, if you go to the right, that's the parental, and then if you move to the left, you become more evolved with time. But you see that the copper contents of all of these, most of them go down. The Andes have some going up, but a lot of them go down. And yet these are the places where you get copper porphyries. So that's the paradox. You have copper porphyries, but the host magmas that eventually give those copper porphyries actually had most of the copper stripped out. That's a funny thing. And then if you go to the island arcs, where we don't usually, and this is where the upper plate is fairly thin, where you don't usually see the copper porphyries, the magmas that come up to the surface actually evolve to high copper. So these go up before they come down, up. We don't, this is Morb, so don't just, so ignore the Morb. It's the Marianas and the Aleutians want to draw your attention to. These actually are rich in copper, the magmas, but they never generate copper porphyry. Okay, so why is it that where you see copper porphyries, the magmas don't have copper, and where you see high copper magmas, you don't see copper porphyries? And so in 2018, a postdoc, Ming Tang, came and worked on some of this, and he took a look at copper contents in arc magmas versus crustal thickness as determined from the seismic data. And there was this negative correlation. This is essentially just telling you and re-emphasizing this paradox, which is when you have a continental arc, so thick crust, there's no copper in the host magmas. But when you have thin crust, you got more copper, but you don't have copper porphyries. So let me take a sidestep here and introduce you to something, a different type of rock now. These are these Christmas tree rocks, green and red, garnet and pyroxene, and they are essentially what we call eclogites, but not in the sense of subducted oceanic crust. These are the deep, deep roots of continental arcs in the Andes, in the former Sierra Nevada, down at 60 kilometers depth or greater. And we, instead of calling them eclogites, we decided let's call them arclogites. And so these are the deep roots of continental arcs. And we thought, well, let's take a look at what the deep roots of continental arcs are in terms of copper or other ore-forming metals. And here, a similar plot that you've seen this before is that this is in the Sierra Nevada. These arc magmas, they start off here with 50 parts per million copper, we think, when they come from the mantle. But by the time they make it to the surface, they've lost a lot of their copper. So where did this copper go? So it dropped down to less than 20 parts per million. You can ignore these lines. They're not so important. They just dropped to less than 20 ppm. So more than 50% of the copper is gone. Well, if you go to the lower plot and you look at these arclogites, right, what we find is, yeah, most of them actually don't have copper, but some of them have quite a lot. The scale is much higher. Some have 300, 400 parts per million. Now, we didn't have many samples. This was a bit provocative at the time to suggest this because, again, we didn't have a lot of samples, but you have to recognize samples of this deep lithosphere or deep crust are hard to get at and hard to interpret. But when we looked at these arclogites, we found the ones that would have high copper, that they were also associated with blebs of sulfides encased within the pyroxenes and garnets. And copper is actually very compatible in sulfides, like pyrite. This is not pyrite, it's chalcopyrite and pyrrhotite. And this is the host that perhaps these magmas had saturated in sulfide, and that actually removed most of the copper back down and into the deep parts of the continent, where it now becomes inaccessible, which is even more interesting now because we still can't explain the origin of these copper porphyries because this stuff is sucking out the copper and not letting it go to the surface. Now, in 2020, more recently, we ended up looking at similar rocks, more from the interior of the North American Cordillera, and these are much nicer rocks, much fresher. And we were able to basically confirm that this was indeed the case, that these copper contents in these arclogites would show an interesting behavior where they start off low and then suddenly they rise up and then cascade down, which is exactly what you predict if you had the sudden saturation in sulfide, and they would just remove all the copper and pull it down to the deep arc, leaving very little left behind to the surface. And of course, to reiterate, the reason why that happens is copper loves sulfides. Its chalcophile goes into chalcopyrite and gravitationally segregates out. And that, of course, is a real problem, because if you remove all the copper through these sulfides, how do you have any copper left to make a copper porphyry deposit? Well, it turns out you have still some, but that copper, it will be bound to sulfide at all times and makes it immobile. But sulfur is an amazing element in the sense that it can morph between two extremes: a very reduced form, which forms the mineral sulfide or the species sulfide, or a highly oxidized form, sulfate, 6+. And so depending on the valence state of sulfur, and petrologists like to talk about this thing called oxygen fugacity, which will control, where you are on this sort of moving bar between reduced to oxidized. But it's not that critical for now. It's just that, are you reduced or are you oxidized? The behavior of copper will change fundamentally. So if you're on the more reduced end, so if you look at oxygen fugacity here, and this is the reduced end where you have no oxidized sulfur, this is all sulfide, and this is all sulfate. In this regime, when it's more on the reduced side, copper would be immobilized. It cannot move because it's stuck with the sulfide. But if you go to the right, with sulfate, the sulfate actually stays in the melt, and the copper therefore does not get segregated out in any phase. And so in this regime, it will be mobilized, and this regime, it can't move. And so all of a sudden we start to recognize that this connection with sulfur means we really have to understand, during the magmatic processes or in the source or at the end, do you move back and forth between this transition? And it turns out Earth happens to, the upper mantle in subduction zones, and straddles this transition here. So it's very sensitive to slight changes in the oxidation state of sulfur can happen very quickly in our terrestrial environments. So let's now zoom even further back out, since we got so deep into like the petrology. Let's go to South America. This is the bend. This is the Andes right here. And what I've plotted here are copper porphyry deposits, where the size of the circle corresponds to the tonnage, the total tonnage, integrated tonnage of copper there. And then I have age color coded here. We decided to look at all these ore deposits and see if there were any interesting systematics in terms of time or structured here, tectonic history, and so forth. And so this is a lot of things right here. But first thing I want to show you here is in all of these, the x-axis is age, so present day on the left, and then you go back in time towards the right. And then the green one right here is the same in all of them. It's the right-hand axis, and that's the frequency of copper porphyries, the number of copper porphyries. And so you can see that in the Andes, 80 million years ago, not many copper porphyries. Then around 30 to 40 million years, you really have a pulse of copper porphyries, and then it disappears, and then goes to not many copper porphyries. So it's not random in space and time, the appearance of these copper porphyries. There's a sweet spot, there's a window. Now, I'm going to go through these now. So in this plot in A, this is the arc front distance from the trench. And so what appears to happen is that the arc front begins closer to the trench. And then with time, it starts to migrate eastward away from the trench. And when it's at its easternmost or furthest away from the trench, you got the copper porphyries. And then it turns out you have a magmatic lull, which is this gray zone right here. Suddenly it stops, not much magmatism. And then it starts over. There's a retreat, comes back and then retreats again, right? Here's the arc front. This is the back arc stuff. And then if you look at some things like strontium yttrium or terbium ytterbium, which are sensitive to the presence of garnet in the history, the petrogenetic history of these magmas, and garnet is an indicator of depth. So the higher the terbium to terbium ratio, for example, that means the higher or the thicker the crust might be. And you can see here is that as you move east, or the arc migrates eastward in towards inboard of the land, it gets thicker. The arc crust is getting thicker. And then you got the copper porphyries, and all of a sudden, everything stops, no copper porphyries, no magmatism, and it starts again, and the crust is getting thicker. We don't have any young copper porphyries here, maybe because they just haven't been eroded, the last few kilometers for us to see. So, why do these arc fronts migrate? Why is there a change in crustal thickness, apparent crustal thickness? And why might this ultimately be related to copper porphyries, which is what we're going to get at. And we did some work with Leif Karlström, and one of the standard views of why arcs migrate, continental arcs migrate, is that you just get flat subduction. Slab shallows, and then of course it migrates eastward, and that certainly has happened and is happening in the Andes. But we tried to take a maybe a more general approach, and that was compare. There is a difference. Really zoom out, look at not just continental arcs but also island arcs. And one of the differences between island and continental arcs is continental arcs always tend to migrate away from the arc with time, whereas island arcs don't migrate. They reach a steady state where they stick with the arc retreating trench, and this distance with respect to the trench stays relatively constant. So it's not migrating, whereas in compressional arcs, they tend to migrate. So the idea is that in compressional arcs, in continental arcs, the reason why they're continental arcs is the upper plate is under compression. And so you have magmatism, you have compression. Those are all both thickening the crust, but also pinching out the mantle wedge here and forcing the place where you generate the hot mantle and the conditions to melt the mantle to go deeper and pushed out away from the trench. And eventually, if you go too deep, you just cut off melting altogether. Whereas in an island arc, the upper plate is an extension, so you reach a steady state very quickly where the crustal thickness is 20 kilometers, not 50 or 60 kilometers, and the trench and the arc distance remains constant. So this is what he was trying to show here through fairly simple analytical solutions. The arc trench distance with time for compressional, which would be the red, and extensional regimes. And so we think this is one explanation for why island arcs are thin, continental arcs are thick, and that may also explain the temporal trends in terms of arc front distance. And the thickness, as it grows, is where then the petrology comes in, because that it dictates what minerals actually will precipitate. And so back in 2017, there was a grad student, Michael Farner, here at Rice, and he decided to look at something that initially we thought, why would we do this? And that was to plot the silica content of arc magmas globally, simply as a function of elevation. Sorry, elevation right here. And there was a correlation. Why would you plot it versus elevation? And why would there even be a correlation between, why is it that when the elevations are high, you get a higher silica contents, almost these dacites over here. And of course, the reason is that on long enough wavelengths, everything is isostatically compensated. So elevation pretty much always correlates with crustal thickness. That's what it's controlled by. And so with this, we were able to expand this sort of connection to crustal thickness beyond what the seismology did, which is only in certain places, just by looking at elevation. And so we got this remarkable correlation in composition with crustal thickness that we infer from elevation. And then we also showed something else, that it's not just the silica. It's for the petrologists here, this is iron versus magnesium. And for the petrologists, the petrologists are always obsessed with, there are some magmas that become iron enriched and some that become iron depleted. And it's the two most important trends in the solar system for rocky planets. But here we're showing that crustal thickness, when it's really thick, everything goes to a depletion in iron. And when it's thin, like an island arc, they go up in this direction. Mid-ocean ridge would go up here to that extreme. So there's a correlation in terms of the chemical composition of what makes it out of the arcs towards the surface and crustal thickness. And we had shown you those relationships with garnet indicators, trace element indicators like terbium, ytterbium, strontium, yttrium. And so Ming Tong has suggested maybe we should just look at garnet. What does garnet do when you fractionate it out to the magma? And of course, we always knew garnet did it because long ago, with the work of Mihai Ducia and Peter Luffy and myself long ago, we've been working on these archaeologites, but for very different reasons. We had seen them, they're right in front of us in the deep arc. There's garnet, but we hadn't really thought about its impact on the rest of the magmas. Well, it took almost 10 years for us to kind of move that direction. And so, at high pressure, you're going to start fractionating garnet. And then what does garnet do? Well, Tang had compiled more data to see if this was really the case. And we look at another garnet indicator, dysprosium ytterbium versus iron magnesium. And we showed that there's this anti-correlation, which shows, that when garnet fractionates, you remove the iron. So the higher the garnet effect or higher pressure, the more iron that's removed. So you have low iron magnesium. Okay. And so iron turns out to be a very, very important element because so sulfur has multiple valence states. But the most important element when we think about these magmatic systems in terms of having multiple valence states is iron. Because there's so much iron, iron can be, as you know, +2 or +3 rust. And however iron behaves could change the oxygen acid, which in turn controls how sulfur behaves. So sulfur follows iron. What controls iron then is the question. So when you have garnet fractionation, it turns out garnet does not like ferric iron. It doesn't take any ferric iron, at least these types of garnets in the arclogites. So then it removes only ferrous iron, and it leaves behind ferric iron in the residual melt as it rises upwards. And so the magma that evolves self-oxidizes. It's an auto-oxidation process, becomes more and more and more oxidized with time. And these are simple models showing if you start from here, a normal type of magma, and you fractionate out garnet, with time, it becomes highly oxidized, a couple orders of magnitude. And at the same time, you remove iron. So you can explain all those geochemical trends with crustal thickness that we've shown. And so far, no one's ever been able to show a consistent model to put all these together and explain them all at the same time. And here we can show that and explain that the consequence is that you would get this auto-oxidation. And we went to see if this is something you see elsewhere. We went to Tibet where you have really thick crust. Magma is going to very thick crust. And this one we looked at the sulfur content in apatite, and this is the sulfur in apatite is only in the oxidized state. So the more sulfur we have in it, the idea was that it was going to be more oxidized. And we showed here that when you have this very strong garnet signature, you had more sulfur, more oxidized sulfur, as measured indirectly from apatite. And so we can model that as you have progressive garnet fractionation, sulfur appears to get oxidized. And so this is the observation. Why? Well, if you go back to the previous slide, we showed that fractionated garnet oxidized the magma in terms of iron. And the link is that when iron oxidizes, it actually controls the behavior of sulfur. So all of a sudden, you have an interesting scenario that when you go to a mature continental arc, the first thing that happens is magmas come from down the mantle wedge, and they're not that oxidized, so they precipitate sulfides, and much of the copper is sequestered down here in the lower crust and entombed there probably forever. Maybe if it delaminates, you'll never ever get it back. But as these garnets continue to crystallize, the magma becomes more and more oxidized, and the sulfides get destabilized and go into sulfate, and that allows what little remains of the copper to be vanquished, released, freed, liberated, so that it can be moved around, and then finally get to a point here that we need other processes. Now that you've liberated, you've got to entrap them again into a reservoir. And so this whole step, this very deep crustal, almost lithospheric scale process, we think is an important step to forming copper. It's not the only step. Many steps are needed. Many things have to align, but it's an important step. If you go to an island arc, you don't get copper porphyries because even though the arc magma is initially enriched in copper, well, it never gets significantly oxidized enough because you didn't form the garnet. And so the copper is never in a mobile state. So in summary, this is kind of what we're thinking. We start off with this cartoon, and this is more of how we envision that, yeah, this is the paradox still, then now we think we partly solved it, is that these continental arcs lose most of their copper, and yet they have the copper porphyries only because we have the oxidizing auto-oxidation of the magma that allows you to finally mobilize that copper. If you follow that, it becomes even more remarkable now that you're making these copper porphyries from very, very dilute background copper. And so the next step is really about kind of the physics of moving fluids and then concentrating in a small part. And that goes beyond what we're currently doing, but I'm going to show you what we're trying to do next to kind of move in that direction. So we talked about this part, the ability to mobilize and scavenge, but we haven't talked about the final step is, yeah, now that you mobilize it, you're going to have to find a way to get it back and put it into a spot. And that is a shallow level process. So we went from very deep. Now we have to also think about the shallow level processes. And of course, we knew that there was always a shallow part of the story because they associate with these textures of porphyries, which are thought to be features that you see only in shallow level intrusions, not deep and not something that erupted, but something that almost erupted or tried to erupt, but just didn't make it. And so something in these textures, which are shallow textures, are telling you that this is the last step that we have to focus on. So recently I've gotten interested, or a group has gotten very interested in these crystals. Like, what can these crystals tell us about the last steps in making an ore deposit? And so we've gone from big scale now come down to this really fine scale of just asking very detailed questions of how do crystals grow, how fast do they grow is actually what we're kind of interested in. And traditionally, when you look at these crystals, if you go and look at these porphyritic crystals, they're almost always zoned. And the traditional way is like, well, these zonations are kind of like tree rings. And with these tree rings, you can tell the entire history of the magma. And of course, that interpretation assumed equilibrium zonation, that every ring faithfully records what's happening in the magma. But there's another extreme, is that if the crystal is growing very quickly, let's say faster than the nutrients to form the crystal or other constituents that are incorporated in the crystal, if the crystal is growing faster than those, the transport timescales for those elements to the crystal, so you can think of that as a high Peclet number. So if the crystal is growing too fast, then there's absolutely no way that it can reflect the conditions of the greater magma. It reflects only local conditions. And the question is, which one is it? And if it's a kinetic control, there are different types of problems you can answer. than an equilibrium one. And so, for example, a highly incompatible element with a fast-growing crystal would generate a very enriched chemical boundary layer, and so you'll get excess enrichments, and then a compatible element you'll get excess depletions. Excess meaning beyond equilibrium. And so the kinetic effects, we can look at the model how these elements get incorporated into the crystal through modeling the boundary layer that forms when the crystal grows at a rate faster than diffusion within the magma. And we wanted to test, is this potentially possible? And we didn't start with the porphyries because they're quite complicated. We went to Hawaii and looked at some weirdo rocks. And they're weird and not really of any interest to probably anyone, except that they have these very, very large acicular olivine crystals, dendritic olivine crystals, which we know means that they grew very fast. And we have some ideas of the cooling rates of this based on how it was in place. So we have some constraints on how long it took to grow these things. And so we basically use this as a natural experiment in nature to see if kinetic effects are ever important in these trace elements. And so that's why we did this. And I don't want to get into too much detail, but here, if you look at phosphorus in olivine versus forsterite, and forsterite content here goes from 90 to almost 100, which is really, really crazy. And you have to use this axis as a measure of the progression of time in terms of crystallization for reasons that are probably a bit petrologic to talk about too much. But the most important thing to look at is the phosphorus content. So phosphorus is a highly incompatible element, and it should not go in olivine. So the equilibrium, we should expect levels down here at the level of 0.00108%. But you can see as the crystal grows, it goes up to 1%, which is pretty much would pretty much set the record for the highest phosphorus content ever measured on Earth. I think there may be another one that's higher that someone else measured, but it's in olivine. It's super high. And of course, I think if people started looking at things at the scale that we did, they're going to find the same thing. But we just happen to do this, and it's incredibly high. And the only way that's clearly not equilibrium, the only way you can do that is with very rapid crystal growth. And so we can look at phosphorus, we can look at titanium, aluminum, all these other elements. We can put them together with their diffusivities and try to get estimates of their growth rates by modeling all of them together. Now, all of these elements up here are incompatible, so they get enriched. And then nickel, you can see, which is compatible, is depleted. And the equilibrium would be 1, this horizontal line. So all of this is showing you that there is no equilibrium and that these kinetic boundary layer effects are dominating here. And so what we got is that these crystals grew at about 1 millimeter per hour, which is quite fast for these olivine crystals. But of course, we knew that these grew very fast, and these would be unusually fast for typical olivines. But it was an extreme scenario. And so what we then decided to do is look at olivines from all over the world, your garden variety of olivines and mid-ocean ridge basalts, arc environments. And there's a lot of information here. All you have to see from here is that there's this lozenge-shaped area that I outlined. And this is what we call the equilibrium array. If you fall on this line, you're slow growth and it's equilibrium. If you fall off this line, it's fast growth. And you can see the great majority of olivine grains that you find in basaltic magmas are all out of equilibrium, implying fast growth. So you have to be very careful to take the composition and interpret them in terms of the chemistry of the magma, which is unfortunate, but you can use them to then say something about the physics, like how fast were these crystallizing. So we've done that, and we can show you here that the growth rates here, if you were to take the disequilibrium levels, and then here are our models. The growth rates are somewhere around 0.01 to zero point 0.1 millimeters per hour. Not super fast, but fast enough. And of course, for us, this is not so important. We just want to know, can we get growth rates? And once you get growth rates, you can then take that and think more about the dynamics of the magma. So we demonstrated that this is all possible with olivines, the simpler things. And so then we went next to pegmatites, where these are formed in these are huge crystals. And of course, they're not the porphyries, but maybe they're related because they formed in these vugs with a lot of fluids around. And this was done by grad student Michael Phelps. And I should say the work before this stuff, I had quite a bit of help also from Chengguan Sun, who's in the audience here and is a faculty member at the main departments at the Jackson School. So in this one, we decided to look at these big crystals. And we did basically the same thing. Of course, here we did not assume a steady state. We did a time-dependent modeling. And here are these quartz crystals in these murallated cavities in these pegmatites where you find these giant crystals. We looked at the quartzes because no one was going to give us these $1 million tourmalines to take apart. So we looked at the cheap stuff. And again, quartz is so pure in general in equilibrium, it shouldn't take anything. So if you look at something like lithium and aluminum, you find actually as you grow from the core to the rim, growing outward, you get this massive enrichment of lithium and aluminum, which is again telling you that, and you get a depletion in one of the few elements that's compatible in quartz, which is germanium. But as you grow, it actually gets depleted. Again, all telling you that these kinetic effects of rapid crystal growth are dominating. And so from this, we were able to show that the quartz crystal grew pretty quickly. Huge uncertainties here, for sure, because there are a lot of unknowns. But on the order of magnitude, what we're getting is that in some cases, it can grow a meter in a day. And these are pegmatites. I think a lot of people are skeptical of this, but if you think about, if you've ever seen one of these bugs, what they are these hydrofracture environments where there's a underground explosion, fracturing everything. And you know that happens. It's just like you frack for oil in the shales. That happens in a split second. And yet these crystals can grow to the size of meters in that time. So in some sense, we already knew that they grew in a meter a day. This is just, making it a little bit more sophisticated there. Now, the pegmatites aren't directly related to the porphyries, but how is it possible that you can grow something like this so big, so fast? And really, it's about how fast you can transport all the nutrients needed to make the crystal. And if you have a static system like a magma, then it moves by diffusion through the magma. But if you have a free fluid phase that is migrating, has an advective component, then you can grow these much faster. And certainly in the pegmatites, it's not just advective. We calculated it's in the turbulent regime, high Reynolds number. So let's go back to the porphyritic system, where if you go to Wikipedia, it'll tell you that these crystals, why they're big is that you sat around for a long time in a static magma chamber, allow these big crystals to grow, and then suddenly they erupted. So it made this fine-grained ground mass. But the problem is these never erupted. They're intrusives. So that can't really be the answer. And so more likely what we think is that you get to a point where this magma, which now has copper that's available, all of a sudden degasses, forms a free fluid phase. And that free fluid phase does two things. One, it enhances the rates of growth here because now you potentially have either a vector component or you have higher diffusivities through fluids like water rather than through a silicate liquid, which is much, orders of magnitude much slower than through water in terms of diffusivity of cations. And at the same time, this dehydration, release of the fluids, increases the melting point. And so without erupting, without even changing the temperature of the magma, you freeze the magma. And that's how you do this. So these things probably grew very fast and then froze fast from degassing. And that degassing step is the last step that is needed to take this copper that's in the melt and move it around to these reservoirs. And I don't have time to go in. There's still more to this. Is how does the copper get into the fluid? We think it's related to chlorine, and we had a recent grad student who just finished working on the chlorine systematics, but that'll be for another talk. So I end with this sort of vision of, even if one didn't understand every single part of the talk, because there are different aspects to it, I just hope that through this, I've shown you that to think about ore systems, you really have to think about the whole system, from the large scale cycling all the way down to even at the micro scale, what's happening at the surface. So thank you very much.
Thank you for the presentation, Cin-Ty. That was amazing. Um, are there any questions from the audience?
Yeah, I have a couple of.
Oh, please go ahead, Tim.
I guess first off, let me thank you. That was really interesting talk. I do want to caution about there are no porphyry coppers in island arcs, because the Solomon chain has at least a dozen. They may not all be commercial, but they're there in Guadalcanal, Bougainville, and then also up in New Britain and New Ireland. So island arcs can form porphyry coppers.
Yeah, no, very good point. And I think uh, it, it's that goes to the question of whether the formation of porphyry coppers. We talk about these very deep-seated processes, and there are some people who think it has nothing even to do with that it is really just what happens at the last several kilometers. And so, and I'm open to that, and I would be the first to admit that, everything I've said here, there's so many unknowns. I can change my mind later on with other things that I see. So hopefully this was just to give an idea of what are some of the processes that might happen. That being said, you have these things in Papua New Guinea and the Philippines, and what is an island arc after all? And I think I may have, so really I should be saying thick arc versus thin arc, rather than continental versus island arc. So you could have an island arc that is mature gone to a mature state and have thicker crust. And I think those could indeed generate copper porphyries through the same processes that I'm talking about here. You might still call it an island arc. So really I should be, I oversimplified by calling things continental and island arc.
Well, once you're actually onto the island of New Guinea, you have continental crust there.
Yeah, yeah.
But one of the things in the Solomons is you do have that, if you will, a double arc, right? There was an older period of arc magmatism which shut,
Yeah.
and that new arc developed in the same place. So that may give you that thickness.
That's right. Yeah, it developed. It developed on the previous edifices, so it can be a little bit thicker. I don't know as much about those as you do, and I think one thing to check is what the crustal thickness is or was at the time these porphyries were formed, and do they have the high strontium yttrium? And I think Luke's must have included those in there, and they have the high strontium yttrium. Of
Yeah, I
course,
saw Pangunum was on there, so.
some people don't think the strontium yttrium is controlled by garnet. So, this is all still highly debated out there, and but it's a good time to have all different types of people come in to this. Yeah, some people think it's amphibole that's controlling the strontium yttrium.
I guess the second question I have is on that slide you were showing the oxygen fugacity, and the slide on the right you were talking about how in arcs you were crossing over the oxygen fugacity boundary. I don't recall you mentioning this, but you did have something up there about lampreyfers. And I guess what do you see as their relation to these systems?
Oh yeah, I didn't mention anything about lampreyfers, largely because I haven't thought about their relationship. I know that usually these lampreyfers are fairly small, but they do occur in some of these porphyries. Bingham, I think, has a lampreyfer, or some of these Colorado ones have them, and I think some even I think Keiko Hattori has even suggested that some of them have very high copper, the lampreyfers. By high, not that you would call it a copper porphyry at all, or ore deposit, but high meaning like 300, 400 ppm copper is still insufficient to be mineable. But she suggested that those are parental, that they may inject into the magma the copper that eventually goes. I don't know. I have to admit I haven't thought as much about them. I don't know what your thoughts are.
So I don't have an answer, but I do know that in the area of Grasberg, a little bit to the north, there's some older intrusives which are lampreyferic. So
Yeah, you know, um, uh, my views have changed a little bit. Well, actually, quite a lot over the years. But when we first did this, and I see Zoltan in the audience there, and he knows Peter Luffy, and Peter Luffy and I had been working on this, our, and we had hypothesized, this copper is segregated, is down in the lower crust and stays there, and we at that time thought that the key to why copper porphyries were found, where you have the really thick crust, is that it was this lower crust, these arclogites would get remelted. And so that would liberate that copper from below, and that's how you get it. And in some sense, it's a little variant of the Atticite hypothesis, but that was focused on the slab, but we provided that. And so if you melt these arclogites, some of them have amphibole, it's not entirely impossible that you could get some silica undersaturated magmas shooting up, like lampreyfers and coming up. So I think there's something there to it. I personally don't think that the lampreyfers are that important for the copper porphyries, but they may be very important for other types of metals.
all right, well, thank you.
Thank you.
Um, I'm afraid we're at time. So thank you everyone for your attendance, and thank you again, Cin-Ty, for the presentation. If anyone has a burning question, please reach out to the speaker via email. And yeah, see you next week.
All right. Thank you so much, everyone.